Okay, welcome to the next lecture of ES 300, Energy and the Environment. Today we're going to do part one of the history of the electric power industry. So here are the quasi-exam questions for not only today, but the next lecture, part two of this history lesson as well. The first question is, how has the electric power industry evolved from its early days to its current form? Question number two is, what are the physical and business financial frameworks of the electric power industry today? And question number three is, how do systems differ by region and state in the United States? So let's start out with the basics of the physical structure of bulk electric power systems. Today, there are three main structural components involved. Number one is generation, the production of electricity at power plants. Number two is transmission, or high voltage transmission of electricity over very long distances. And then there's distribution of electricity at lower voltages, which delivers the electricity ultimately to end consumers. So this is what that looks like. We have power plants that produce the electricity. Here the power plant is represented by an image that we all tend to associate with power plants, a big cooling tower. And the electricity that's produced is then ramped up to very, very high voltages at transmission substations, and then the electricity is sent or transferred over long distances via high voltage transmission lines until it gets to the general area where the electricity is to be consumed. At that point, the electricity is ramped down, the voltage of the electricity is decreased, and then it is sent out at a lower voltage along distribution power lines until it gets to the point of consumption, for example, businesses or people's houses. So there are four eras in the electricity industry in the United States that got us to this point where we have the physical structure that I just described. So let's talk about those four eras now. The first one that lasted roughly between the 1880s and 1910, we refer to as competition, brutal and inefficient. These were the early days in the electric power industry. And this was a time period where a lot of the more fundamental questions about how we were going to make, distribute, and sell electricity during the 20th century were answered. The second period was 1910 to 1970, the natural monopoly consensus. This was a very long period over which the structure and the business model of the electric power industry really didn't change. And it ended in the 1970s for a couple of reasons that we'll discuss. And from 1970 to the early 2000s, we had the first wave of restructuring. And then since then, the electric power industry and electricity markets have continued to evolve, including the integration of new technologies. So we're going to talk mostly about 1 and 2 today, and we're going to talk about 3 and 4, or 3 the next time, and 4 will be sort of an ongoing discussion throughout the rest of this class. So let's start with the period of initial competition, 1880 to 1910. These were the early days of the electric power industry. The first power plant that was operational in the United States was operated by Thomas Edison. It opened in 1882. It was called the Pearl Street Power Station, and it was located in Lower Manhattan in New York. This is a picture of the generator that was used within the power plant to produce electricity. It was called a jumbo dynamo. Edison's jumbo dynamo produced electricity that used a direct current, and it was a steam generator. So a steam generator is a class of power plants that we still rely on quite a bit today. So this is a schematic of how steam generators work. There are 4 main steps here. You can see number 1 is having some sort of fluid. And then that's usually water, and that fluid is passed through a pump which pressurizes the water, and the water is passed into a boiler where there is some source of heat, QN, and usually when we're talking about power plants, that source of heat is coming from the combustion of a fossil fuel like coal or natural gas, or in the case of a nuclear power plant, a fission reaction. So that source of heat is used to boil the liquid, so to turn the liquid into a gas. And at step number 3 here, that gas is allowed, or the steam is allowed to expand. And as the steam expands, it does work. It spins a turbine. And that turbine is really just a coiled conductor that is situated within a magnetic field. And when you spin a coiled conductor within a magnetic field, it generates current. So that's the electricity that the plant would be producing. So also, as the steam expands, it starts to cool a little bit. And then in step 4, we want to cool it down even more, usually by passing the steam across some sort of condensing coil in which there is cool water being passed through. And so we are capturing that steam and returning it back to its liquid phase. And then that liquid starts right back at the beginning. At point number 1, it's passed through the pump and heated up again into steam to generate more electricity. And this is just a schematic of a simple DC generator. We have a coiled conductor that would be spinning within a magnetic field. In the case of a fossil fuel power plant, the force that is spinning the coil would of course be the steam expanding, which ultimately we're getting that movement by combusting or burning some sort of fossil fuel. So Edison's jumbo dynamo weighed about 27 tons. It produced about 100 kilowatts, so that was at the time enough to power about 1,200 light bulbs. And this first power plant operated successfully in the United States until 1895. So during this period of initial competition from 1880 to 1910, there were 2 major outcomes that really set the stage for much of the 20th century in terms of how the electric power industry developed. And the first major outcome was the decision of what type of current we were going to use, AC or alternating current versus DC or direct current. And the second major outcome was what the geographical organization of electric power infrastructure was going to be. So the decision about whether to use AC or DC power is infamous in American history and in the history of the electric power industry. It involved sort of 2 major opposing forces, scientifically and from an engineering and business perspective. One that was a proponent of using AC systems and one that was a proponent of using DC systems. In this period, this decision process is referred to as the current war. And it has been popularized in books and movies, including a recent movie called The Current War that stars a lot of well-known actors. It looks like the Rotten Tomatoes tomato meter doesn't give it a very high rating, although the audience likes it. So if you're interested in sort of a pop culture take on The Current War, you could go check this movie out. And actually, a number of the actors, all of the main actors in this movie, also happen to be in superhero movies. And so I'm going to attempt to give sort of the Cliff's Notes version of The Current War in terms of the participation of these superheroes. So the current wars, as I mentioned, involved sort of 2 opposing forces. The first was the Westinghouse Electric Company, and the other was General Electric. So the Westinghouse Electric Company was the owner of Nikola Tesla's patent for the alternating current AC electrical supply system. And in the movie The Current War, Tesla is played by the same guy who plays the Blue Beast in the X-Men movies. In the other opposing force was General Electric Corporation. It was created from the merger of the Edison Electric Company, which was owned by Thomas Edison, and the Thomson-Houston Company. In the Current Wars movie, Thomas Edison is played by Benedict Cumberbatch of the Sherlock fame, as well as Doctor Strange. So the current wars were this conflict between the proponents of 2 different types of current, alternating current and direct current. Westinghouse, the owner of the Tesla's patent for the alternating current supply system in the current wars, is played by the bad guy from one of the new Superman movies. So before we get into this, let's go over some basic physics that I think will help us understand how the decision was made to go with one current versus the other. So just some terminology from basic physics. Voltage, measured in volts, describes the difference in electrical potential between 2 points. Current measured in amps refers to the flow of electrical charge. In electrical circuits, this charge is carried by moving electrons in a wire. Resistance, measured in ohms, refers to the measure of an object's opposition to the flow of electrical current. And then power, measured in watts, is the rate per unit time at which electrical energy is transferred by an electric circuit. So a couple laws. Ohm's law states that voltage in a circuit is equal to current times resistance. Power equal to current times the voltage, and power losses along a wire is equal to the resistance of that wire times the current squared. So early DC systems, power systems, generated and then distributed electrical power at the exact same voltage as that used by the customer's lamps and motors. So let's look at an example of a really simple DC circuit that might be something that looked like Edison's DC system. So we want to figure out what the voltage is at the load, which is the source of electricity demand, or in this case, a light bulb. And so we have this picture of a simple electric circuit. Instead of a generator here, we just have a voltage source, which is the battery. And so our voltage source here, let's say, is 100 volts. So we have two sources of resistance in this circuit. The first would be the load, or the light bulb, the demand for electricity. This is we're going to say is an incandescent light bulb. So it's producing light by heating up some sort of filament by passing electricity through it. And the heat is opposing the flow of electrons here. And so that is one source of load, and we're going to say, or one source of resistance. And so that is one source of resistance. And we're going to say its resistance is 1 ohm. The other source of resistance here is the wire itself. So the wire that is transmitting the current, passing the electrons through, is a conductor, which means it's good at passing electrons through, but it's not a perfect conductor. So it is also associated with some resistance to the flow of electrons. And so we're going to say the resistance of the wire here is 0.5 ohms. So if we want to figure out what the voltage at the load is, the first thing that we have to do is figure out how much current will be flowing through the wire. To do that, we use a version of Ohm's law, V equals IR, but in this case we're going to consider R to be the cumulative resistance of both the load and the wire. So the voltage is the source of the battery, so 100 volts divided by the cumulative resistance, so the resistance of the light bulb and the wire added together is 1.5 ohms, so 100 divided by 1.5 ohms gives us 66.67 amps. So that's the current that's available that's flowing through the wire, that would be flowing through the wire at the load, at the light bulb. If we want to figure out the voltage at the load itself, we just have to multiply that current that we just found times the resistance of the light bulb itself, which is in this case 1 ohm. So the voltage at the load is just equal to 66.67 amps times 1 ohm, or 66.67 volts. So one of Edison's problems in using his DC system is that when more customers were added, the length of the wires increased, and that means that the resistance of the wire increased. And as more customers were added, more light bulbs were added, which means that the cumulative resistance of all the different loads on the circuit were also increased. So let's go back and take a look at what increased values of RW and RL would do to this system. So if we want to see what the voltage, how the voltage at the load would be affected by longer wires and more sources of load, all we have to do is look at that first equation where we're trying to figure out what the existing current would be at the load. So if we're increasing the voltage, the number of loads on the system, the number of light bulbs that are being powered, and we're also increasing the resistance in the wire, the denominator of that first equation where we're trying to figure out what the current in the circuit is, would increase. And so our value of I, the current in the circuit, would get smaller and smaller. And then if we want to look at what the actual voltage available at any given load would be at the light bulb, what that means is that because the current is lower, then the voltage available at the light bulb would get lower and lower and lower. And so this was a problem. What it meant is that as more customers were added, the increased resistance, cumulative resistance of the wires and the load meant that there was less voltage available at the point of consumption. And what that meant is that Edison's customers had to live within a few miles of a power plant. Otherwise, the voltage, by the time the electricity got to the point of consumption, the voltage would be so low that the light bulbs wouldn't even be able to be used. So Edison's challenge in designing a DC power system was twofold. Number one, he had to figure out how to design the system to be able to support more light bulbs without dropping the voltage, because he wanted to sell electricity to as many people as possible. And he also wanted to be able to sell electricity to customers that lived far away. So one theoretical solution was to increase the voltage at the source. So one theoretical solution was actually to increase the voltage at the source. So let's say we have this power plant, this generator that produces electricity, produces power, and we represent the amount of power that is being produced as equal to current I times voltage V. And whatever solution we come up with here, we want to keep the power the same. We want to be able to produce the same amount of electricity. And so if we use that equation, P equals IV, we can get the same value, let's say 100 here, a couple of different ways, right? We could have a really high current value for I and a really small voltage, a value of V, or we could have a really, really low current value of A and a really, really large voltage value V. And that's what these two examples show, right? So we can get 100 in terms of watts power by multiplying a current of 4 amps times a voltage of 25 volts. Or we can get that same power by multiplying a much smaller current of 0.04 amps times a voltage of 2,500. So in this case, what it shows is that we can increase the voltage by 100 times, and that allows us to decrease the current by 100 times while keeping the actual production of electricity or power identical. And so this was really helpful, because what that means is that a higher voltage implies that less current needs to flow. And by increasing the voltage, it reduced the resistive losses on the transmission lines. So the loss of power along transmission lines, remember, is given by the expression of P equals I squared times R, or resistance. So because we're squaring current here in determining what the power losses are on transmission lines, and so what that means is that relatively small increases in I, or current, can result in larger and larger thermal losses of power on transmission lines. But if we increase the voltage significantly, and that allows us to decrease the amount of current that we're sending on the circuit, that's a way for us to keep this value of thermal losses on transmission lines, or P is equal to I squared times R, as small as possible. At the same time, the voltage drop across the wire from adding more and more light bulbs isn't as significant, because that voltage drop we quantify as V equals IR, and if I is really, really small, that means that the voltage drop is also small. Now, the problem was that at the time, no one knew how to adjust the voltage of DC systems, but we did know how to increase the voltage of AC systems using relatively simple transformers. And what this meant is that AC power could be sent long distances over relatively small wires at a convenient high voltage, and then reduced in voltage at certain points for end use by customers. So that strategy should look a little familiar. That's what we talked about earlier in the lecture. We have power plants that produce electricity at a lower voltage. Then that voltage is increased, ramped up using a transformer, and it's sent out over transmission lines at very high voltages in order to reduce power losses, resistive losses on the transmission lines. Then it gets to power substations. The electricity is ramped down to lower voltage and then distributed at that lower voltage to end-use customers. So one of the really important implications of this is that AC generating stations could be fewer and larger. So we didn't need power plants to be interspersed With population centers, they could be located more distantly away from where people lived, and the electricity sent longer distances over high voltage transmission lines. So a question for you. If we are building power plants, we're building fewer power plants and we're building them bigger and bigger, what economic principle does it sound like we were able to take advantage of here? So here's a hint from one of the first lectures we had in this class, and what it shows is that as the number of individual units that you're able to produce increases, the average cost decline, and that's because the fixed cost is being spread out over more and more individual units sold. So the same thing in theory could be true of producing electricity. If you were able to build fewer power plants and then at those individual power plants produce more and more electricity, you could reduce the average cost of electricity sold. So again, we call this economies of scale. And I mentioned earlier that this was hugely important to the historical development of the electric power industry. So one of the other things that this allowed power producers to do was to locate power plants far away from other people. So if you're looking at this figure, what do you think was another benefit of high voltage systems, the AC power systems? And thinking about this from the standpoint of human health, the obvious benefit is that whatever's coming out of the power plant smokestack was further away from people. And at the time, the primary fuel was coal. And by combusting the coal, you were dumping a lot of nasty stuff in the atmosphere. So high voltage systems allowed us to put power plants away from people and minimize the human health risks that generating electricity could have. So ultimately, the lower cost of AC power distribution prevailed. Even though DC systems persisted in some urban areas throughout the 20th century. Just a side note, the DC systems, especially high voltage DC, are now making a comeback in some areas. They can be more efficient and make it easier to integrate variable renewable energy like wind and solar. And so this is what part of your reading for this time touched on. So that was one major outcome that helped set the stage for much of the 20th century, was the type of current use. And because of its lower cost, its ability to take advantage of economies of scale, which was made possible by the knowledge of how to increase and decrease the voltage of electricity in AC power systems, AC systems were selected. Now, the second major outcome was the geographical organization of power system infrastructure. Let's talk about that next. So during this period of initial competition, you had lots of overlapping distribution lines and really fierce geographical competition for customer bases. For example, in Chicago alone, over the period of 1887 to 1893, there were 24 central power companies that were established in order to serve electricity to customers. And so I couldn't find a photograph, but this is an artist rendition of what the streets of Chicago looked like at this time with all these power lines overlapping. So something had to be done, and there was only one person for the job, and that's Spider-Man. Not really, but in the movie, Current Wars, the character of Samuel Insull is played by the same actor who plays Spider-Man in the most recent iteration of those movies. And so Samuel Insull, in 1898, acquired a monopoly over all central station production of electricity in Chicago. And so Samuel Insull is famous for believing that the electric power business was what we would call a natural monopoly. And that's in other words of saying that there are economies of scale associated with electric power production. So here's a quote from Samuel Insull, and he says, "Exclusive franchises should be coupled with the conditions of public control, requiring all charges for services fixed by public bodies, so regulators, to be based on cost plus some sort of reasonable profit." So what is he really suggesting here? What he really wants to do is allow one company to sell all the electricity for a given geographical area, for example, North Carolina, and require that utility to sell the electricity at cost plus some sort of guaranteed modest profit. And what we're also going to do is protect those utilities from competition. And the hypothesis here is that if we allow one utility to do everything, that costs should decline because we're able to take advantage of economies of scale. So why? At the time, the dollar per megawatt hour cost of electricity from a small plant was actually higher than that of a big plant because of economies of scale. The bigger plants are able to spread the fixed costs associated with the infrastructure over more and more individual units of electricity sold, and so the average cost of electricity declined at the larger the power plant was. There was also redundancy in infrastructure. It cost money to build overlapping transmission and distribution lines. We didn't need all of that. And there was also potentially lower business overhead from just operating one company as opposed to several. So again, the whole idea here is that there are inherent economies of scale involved in the electric power industry because it's so capital intensive. You do not want more than one company trying to sell electricity in the same place at the same time. If you just allowed a single company to do it, if you allowed monopolies to exist, you would get lower prices of electricity. And what was the key to all of this? Tesla's invention of the AC transformer and the superiority at the time of AC power systems. It made it possible to build large power plants and build them away from other people. And in order to take advantage of those economies of scale, it made sense to treat electric utilities as monopolies. It became this rational economic choice. The best chance to reduce the cost of electricity for people was to allow electric utilities to operate as monopolies over geographical areas and have complete control over the provision of electricity to customers within a given geographical footprint. So this became the monopoly consensus from 1910 to about 1970. Electric power utilities operated as what we would call regulated monopolies. So utilities were granted monopoly rights over geographical areas. Electricity prices for consumers were regulated by utility commissions. So these were part of state government, and their job was to ensure that the rates that were charged by the monopoly utilities were fair, but they also made sure that the utilities could earn a profit or a solid, predictable rate of return. And so this is the model that we still have today in North Carolina. Duke Energy is a regulated monopoly. And in North Carolina, the regulated body, and in North Carolina, the regulatory body that is in charge of overseeing the decisions that Duke Energy makes about building new infrastructure, as well as the decisions that Duke Energy makes about setting prices for electricity for retail consumers, is the North Carolina Public Utility Commission. So this regulated utility model, in other words, the whole idea of allowing utilities to operate as monopolies and protecting them from competition, and regulating them using these utility commissions, these public bodies, had lots of other benefits too. The utility commissions guaranteed that utilities could recover their costs and earn a stable profit. And what that meant is that if they needed more money to make the profit that they were allowed to make, they could actually increase prices on customers. And so that might sound kind of greedy, but effectively what it meant is that utilities had sort of a guaranteed way to stay financially healthy. And so go back to our first lecture when we talked about basic accounting and project finance. We talked about the importance of financial health to a utility or any type of business that is financing infrastructure or borrowing money to build stuff. Remember the relationship between financial health and interest rates on debt. If you are borrowing money and you are not a financially healthy company, the people that are going to lend you money are going to charge you a higher interest rate because you're going to have a lower credit score. And so the regulated utility model as a method for allowing utilities to stay in good financial health by protecting them from competition and allowing them to increase prices on customers if need be in order to maintain solid financial health was actually a way to keep the interest rates lower on the debt that the utilities borrowed in order to build infrastructure. And ultimately, that meant that the total lifetime cost of the infrastructure involved in the electric power industry was able to be cheaper. And what that meant is that the cost of electricity to individual customers was cheaper. So this figure at the bottom here, it shows you what the dollar per megawatt hour cost of electricity was for that example coal plant using a 4% weighted average cost of capital versus a 5% weighted average cost of capital. The higher average cost of capital, so the combined interest rate on debt and return on equity for shareholders, the higher that is, the higher the price of the electricity has to be in order for the utility to make its money back. So staying financially healthy is a way to lower electricity prices for customers. So did this strategy work? Let's take a look. It did. It worked like a charm. From the early days of the electric power industry until about 1970, the price of electricity dropped precipitously. And you can think about everything that happened in the United States over this time period. I mean, a decreasing price of electricity was extremely important to the economic development of the United States. At the same time, this was a win-win for investors. The ability of utilities to earn a guaranteed profit, potentially by increasing prices on customers if need be, made them a really good, safe investment for investors seeking stable long-term returns with minimal risk. So that would be people that wanted to buy bonds that are issued by utilities. Buying bonds, the interest rate was pretty low, but you were pretty certain that you were going to get your money back from the utilities because they were seen as sort of safe, financially healthy organizations. And also buying stock in utilities was seen as a pretty good investment as well. So remember earlier in the semester where I sort of poked fun at these people? These were fixed income investors. This is just an advertisement for Duke Energy's website. So fixed income investors, again, are investors that buy debt. They buy bonds that are issued by Duke Energy. Another way of saying that is that they lend money to Duke Energy and expect to earn that back with interest. And sort of I suggested that they were complicit in carbon emissions and the use of fossil fuels because they're helping to finance a coal plant. So what we've sort of learned today is that, yes, that's sort of technically true, but another way of stating that in a slightly more magnanimous way is that these, bond buyers, people that buy bonds that are issued by Duke Energy or lend Duke Energy money, are actually a way for Duke Energy to provide affordable and reliable electricity to people in North Carolina. Now, that doesn't mention anything about the environmental impacts, but the mission for a really, really long time did not involve environmental impacts. And I realize that's sort of a problem, and we're trying to correct that quickly at this point. But at least at the onset of the electric power industry, and for about 50 or 60 years after that, the mission was really just to provide cheap, reliable electricity. And in that respect, this was a huge success.